At the University of the Azores have been collaborating in organizing a series of scientific events related to astrophysics and space science. And even though they are mostly scientific meetings, we are aware of our social responsibility, and we've been from the beginning trying to get the rest of the community involved. So trying to explain to the other people what we do, so rather than isolating ourselves in a room for a week and talking about science, that's fun. Make some effort to explain to people what we are discussing, why that is relevant, so things we're working on. And of course, we take the opportunity that we have internationally renowned scientists that are leaders in their field to take the opportunity that they're here and ask them to explain a little bit of the work that they do. So this is something we've been doing, and we're quite proud of that fact. And of course, we're also happy that people here, the younger municipality, other entities have been quite welcoming to this idea of ours. So in this case, OASA has been collaborating, the library has been quite receptive to our suggestions, so we're very happy to be here. So this is the first of a series of 3 talks. So we have a talk tonight, another one on Wednesday, and another one on Friday. Also on Friday there'll be a parallel talk at OASA in San Miguel. So the talks will aim to explain a little bit various aspects of cosmology, which is what this conference is about. So the idea is for you to understand what people are working on, what we scientists find exciting topics, and try to communicate a little bit of that excitement to the rest of you. So tonight we'll have Joe Liske talking about gravitational waves. So Joe comes from Germany, although he did his PhD in Australia. Then he spent some time in Scotland, in Edinburgh and St Andrews. Then he worked at ISO for more than a decade, and about 2 years ago he moved to the University of Hamburg, where he's now a professor. And some of you may recognize him from the ISO video casts, so he's Dr. J, that you might have seen on a number of videos. So tonight we have here in person, so we'll tell a little bit of gravitational waves, and then you can ask them everything you want about astronomy. So over to you, Joe.
Thank you, Carlos. So thanks for the invitation to be here. When Carlos asked me to come to the school, I immediately said yes, even without checking my calendar, whether I could actually make it, because all my life I've wanted to come to the Azores. It's been for decades now, and we already had, my wife and I had already made quite firm plans about 10 years ago, and then she got kicked by a horse, and we couldn't go. So now I'm here, so I'm very good, very glad. Okay, so let me start tonight with this quote here. We live in a golden age of astronomy. And you'll note that the quote doesn't have an attribution. I'm not telling you who said this. And the reason I'm not telling you is because I don't know. Because it's been said so many times in the past 20 years that it's become sort of a standard trope almost in astronomy. It's been said in many different contexts. In particular, it came up a lot in the 1990s when there were a lot of space observatories launched and large ground-based, the first 8 and 10 meter class telescopes on the ground came into operation. And there was a lot of synergies between these various observatories and that really ushered in a golden age of astronomy. And in particular, it ushered in for the first, well, almost for the first time, the fact that astronomers that operate in different parts of the electromagnetic spectrum, so radio astronomers and X-ray astronomers and UV astronomers and optical astronomers and infrared astronomers, so they came together and brought together their data to investigate the objects in the universe. So the 1990s really saw the birth of what we call multi-wavelength astronomy, bringing together data from the entire spectrum of electromagnetic radiation. What I'm talking about today, really, and what we've seen now in the last few years, is going even a step beyond multi-wavelength astronomy to what we've come to call multi-messenger astronomy. And what I mean by that, I just want to spend the first 5 minutes explaining to you. So let's go right back and ask ourselves, how is it that we can find out anything about the universe at all? How do we get information about the universe? What transports that information? What are the messengers that bring the information about the universe, about distant objects to us? Well, the first thing is pretty obvious. That's the first thing that comes to mind when you think about astronomy generally. That's light, or rather, in physical terms, it's electromagnetic radiation. So the light that we see with our eyes is just one part of the electromagnetic spectrum, but there's light, infrared light, UV light, radio light, all of this other electromagnetic radiation is there as well. And that's what I was just talking about on the last slide, bringing all of that together. That was multi-wavelength astronomy. But there are other things, of course, that we can do. Well, of course, there's also direct exploration. So you can actually try and send a robot or a probe or a vehicle of some sort or a space probe to the object of your interest. But it should be pretty obvious that that doesn't work that only works for essentially the solar system, right? It's very difficult to send, we've never even sent an object even to the very nearest star to us. That doesn't work. But direct exploration, I'll just remind you even very briefly of the amazing achievements that we made in this area in the last decade, or last couple of decades or so. So this is a great plot that I really love, out of this world record. So what this plot shows is the driving distance on the Moon and on Mars that various vehicles have driven on the surface of these of either Mars or Moon. So right up there is Opportunity. So you may remember Opportunity and Spirit. Those are two Mars rovers. Spirit is long dead, but Opportunity is actually still alive and still going. And as of January 2017, it's traveled almost 44 kilometers on the surface of Mars. That's really amazing if you think about it. This is more than a marathon, so we have an object on the surface of Mars that has traveled for longer than a marathon. I'm sure there's somewhere, I'm sure you can probably come up with an index of how advanced the technology of civilization is by measuring how long you've driven on the surface of another planet, something like that. Anyway. But even Opportunity, Curiosity, which has by last month, July 2017, has driven 17 kilometers, and it's only landed 5 years ago. So in 5 years, it's done 17 kilometers. It's quite amazing, actually. On the website of NASA, you can actually look up daily reports of what Curiosity is up to, and this is the path that Curiosity has taken on the surface of Mars. It's mind-boggling, right? I mean, 30 years ago, if you'd shown somebody a map like this, they would have said you're crazy. And it brings the stuff that we've learned about Mars and about our neighboring planets is quite amazing. You see these panorama shots that have been sent back by Curiosity. But even more amazing things, you know what this is? You know what this bit is here? That's a meteorite. That's a meteorite on the surface of Mars. So finding meteorites on Earth is usually, it's a reasonably big thing, okay? The other day I had a neighbor came to me with a rock and said, "Is this a meteorite?" I said, "No, I'm sorry." I was very disappointed. But finding a meteorite on another planet, how cool is that? So this is actually an iron meteorite. If you look very carefully, you see these 5 white dots on there, and they seem kind of regularly spaced. That's because those 5 white dots are not actually natural. That's where Curiosity, where the rover, zapped the meteorite with a laser to find out what it's made of. Come on, that's science fiction, right? That's amazing. So you have a rover there that shoots a laser at meteorites. That's just incredible. This picture is a picture of Pluto, taken by the New Horizons spacecraft about 2 years ago. That was the New Horizons, I'll remind you, was the very first spacecraft that ever went to Pluto. You kind of, we've all grown up, there's nobody old enough here, but we've all grown up in the spacefaring age, and we seem to think, having grown up with all the news of various spacecrafts going around there, you kind of think that probably the solar system is probably very well explored by now. That's actually not true. Again, New Horizons was the very first spacecraft that visited Pluto, and it was just a flyby. It didn't go into orbit. That's much too difficult to go into orbit around Pluto. You can't do that. It was just a flyby, so it had just one chance, just flew by, took a bunch of pictures, and off it went into deep space. Okay? So that's amazing. And now something's actually happening in just 2 weeks from now. The Cassini spacecraft that has been out at Saturn for quite some time now is now nearing the end of its mission. It's now going through what is called the grand finale orbits. And what it recently started doing, it started going into these orbits and taken very high up across the poles of Saturn, and then it dove right in between the rings of Saturn and the planet itself. First time we've ever done that, never been done before. Quite amazing. They were so afraid because they had no idea what's actually there. They were so afraid of debris between the rings and the planet that they turned the spacecraft around so it would go with its radio antenna first, so it wouldn't get that much damage. But then it was discovered, well, there actually isn't very much debris. Next time they flew through, they could just, went in open-eyed, essentially, to take pictures. Quite amazing. And in just 2 weeks, Cassini is finally going to reach the end of its life, and it will actually slam into the surface of Saturn. Well, surface, I mean, into the atmosphere of Saturn, and will die in there. So we will actually get some few the very last shots from Cassini will be very close up of Saturn. So a lot of things are happening in the realm of direct exploration. But beyond that, so with electromagnetic light, direct exploration, those are things that we're quite familiar with. So now let's move into the territory that most people are not so familiar with. And the first thing to talk about is a cosmic ray. So cosmic rays are essentially particles, or charged particles, that stream throughout the universe. To some extent, we're still not sure where these particles are produced and where they are accelerated to the enormous energies that we observe that they have. And when they hit the top of the atmosphere, they generate a particle shower through the atmosphere, and they generate little flashes of light. And these things we can actually detect. We started detecting this about 10 years ago, 2005. The Pierre Auger observatory, the largest cosmic ray observatory, started operations, and this is in Argentina. So there's a whole bunch of water tanks here that can actually detect the particles as they hit the ground, and then there are little telescopes around the perimeter of the site that can actually see the little flashes of light that happen in the atmosphere. So we are now actually using cosmic rays as a tool to tell us something about the universe. But this is difficult. Because cosmic rays are charged particles, it means that they can be deflected by magnetic fields, and the universe is full of magnetic fields. And so even if you could determine precisely what direction on the sky a charged particle came from, that doesn't mean it tells you that I know where that cosmic ray actually originated, in what object, because it may have taken a zigzag path through the universe. So this is difficult. Next up is neutrinos. What is a neutrino? Neutrino is an elementary particle that is a very ghostly type of particle. It almost has no mass. It doesn't participate in most of the interactions that most matter participates in. So what that means is that it's very, very difficult to detect. But we can detect it, and there are neutrinos coming from us from space. In fact, there are enormous numbers of neutrinos coming from space. There are even from our own sun, there are, I forget what the number is, but there are millions of neutrinos crossing every square centimeter of your skin every second. And the reason you do not realize that is because they don't interact with you. They go straight through your body. In fact, they go straight through the entire Earth without interacting anything. So you can actually look down and I can see neutrinos. If I had the right detector, I could see neutrinos coming right from the other side of Earth, coming right through the Earth. So this is also difficult, but we do have a neutrino observatory. It's called IceCube, and it's situated at the South Pole. And what people did is they took a cubic kilometer of ice and melted it and turned it into water. And then they hung these lines in here, and on each of these lines there are these optical devices called DOMs. Here you see them. And then they refroze the ice, okay? And so they're now using this cube kilometer, so 1 kilometer by 1 kilometer by 1 kilometer, no, 1 kilometer, this massive amount of volume. So that ice cube is now hence the name, is now the detector for these neutrinos. So the idea is a neutrino comes, interacts with the water ice, a little flash of light is generated again, and that flash of light is then detected by these optical devices here. So again, you can see This now works, it's been in operation since 2010, it's now being upgraded in fact. And we do see neutrinos with this, not very many mind you. So during the space of 3 years I think they saw a total of 32 neutrinos. So again, this is difficult because neutrinos just simply do not interact with anything, so they are very difficult to detect. But we do astronomy now, right now, and in fact there's somebody here at the conference, but he's not here at the talk, who actually does quite a lot of science with this and just got a big bunch of money to do even more science with this. So, cosmic rays and neutrinos and all of those things we've been doing since that we've been doing for several hundred years, even 1,000 years, that we've been doing for a few decades. This has been, we've been doing over, say, in the past 10 years now. And what is now new, and what is the main topic of today, is of course gravitational waves. And the detection, and the direct detection of gravitational waves is really now completing this set of messengers, the set of information carriers that we can use to find something out about the universe. Okay, we've now, these are all the messages there are. Okay, that's all the things that we can use to learn anything about the universe. There's nothing else. It's those 5 things. Okay, and now with the detection of gravitational waves, we finally completed this, and we're now well and truly in the era of multi-messenger astronomy. So trying to find out about the universe and about objects in the universe using not just light, but using all of these different, minus this, but using all of these information carriers, and thereby trying to find out even more about the universe than we already know. Okay, so that's what said multi-messenger astronomy. That's where we are now, and that's the rise of that is what we'll see over the next decade or so. Okay, so now let's talk about gravitational waves. What is that? And of course, you have to start the talk about gravitational waves with this gentleman here, Albert Einstein. I'm sure you all recognize him. And he, in the year 1915, came up with a theory called the general theory of relativity. And what that theory essentially is, it's a theory of gravity. It tells us how gravity works. And it was a controversial theory at the time, but since it has been proposed, it has stood the test of time. It has stood all the experimental tests that we know of. We know it's not the final answer. We know it's not the final theory of gravity, because it's not a quantum theory, but that, never mind. On large scales, it's passed all of the tests, and it is our best description to this day, even 100 years later. That's quite amazing. There's not many physical theories that have lasted for 100 years in modern day. It is still today our best description and our best understanding of how gravity works. Okay, so I want you to keep that in mind. So, like I said, this was in 1915. He published this first. So that means in 2015, of course, we had the centennial, which had a big reaction in the press, and there were lots of events celebrating this. This is the original paper, by the way, which was published in the Prussian Academy of Science in Berlin on the 25th of November 1915. It's the birthday of my wife. Well, not the 19th, the 25th. So this is the first publication where he got the equations, the central equations of general relativity, where he got them right. He had a few attempts before where they weren't quite right yet, and this is the first time he got it right. Okay, so gravitational waves has to do with the general theory of relativity. And the key point to understand is that one of the key things, and that's one of the reasons why it was so revolutionary, what Einstein did in gravitational in general relativity was he did away with the notion of space and time, but forget about time for a moment. He did away with the notion of space being somehow a static stage on which the laws of physics are being played out. Instead, he replaced it with a concept of space being something that you can form and that is malleable and that can change. Okay, the best way to think about it is really an analogy like this. So the idea is that if you have an object with mass, which in the previous thinking, in the previous theory of gravity, you would the idea was that this massive object is exerting somehow gravity. In Einstein's theory, gravity isn't really a force. What Einstein really thought of gravity, or that what the mass of an object does, it deforms the space-time actually around it. And if you have another object then that is close by, all that other, if you take a little test particle, all that this object is doing is not actually experiencing a force exerted by this object. All it's doing, it's following, it's just traveling through this curved space-time. And an object that is traveling through a curved space-time looks like an object that is no longer traveling along a straight line, but doing a curved thing. Okay, so you can imagine that an object that falls in here is actually will be orbiting this thing, but all it's doing is actually following a straight line in this curved space. Okay, so Einstein. So the key point to take away simply is that Einstein replaced the idea of space being somehow a static thing that in itself doesn't even have anything to do with the laws of physics. He replaced that and with the concept of where space is actually part of the physics, okay? And it's not only part of the physics, but space is somehow a quantity, an object that you can form, and that is changed, the geometry of this space is changed by massive objects. Now this is a static scene here, but it should be pretty obvious. Well, what happens then if I make this object move? Well, if I make it move around, then obviously the geometry and the curvature of this space will also change. And it just turns out, if you do the maths in the equation, it just turns out that there are some situations in which you can actually generate a wave which will propagate through the space. Okay, so that's what is seen here. So here you've got two masses, and they're orbiting each other, and the field equations by Einstein predict then that if you have a situation like this, that you get a ripple going through space-time, being transported through space-time, and they actually transport energy, as we will see later. And this is just a dynamic situation, and so it's not just a static deformation of space-time, but actually dynamic deformation of space-time. And in this case, it's actually waves emanating outwards, just very similar. And you can imagine it, and that's what it looks like. It's very similar. Like if you drop a stone into a pond, in the center of a pond, and these waves just propagate outwards from where you drop the stone. So what happens? What do I experience if I stand in the way of a gravitational wave? So imagine I stand here and this gravitational wave is coming at me. What do I experience? How should I picture this? The way to picture this is shown here. What a gravitational wave does, it stretches and or compresses space in the directions perpendicular to its propagation. Okay, so in this case we have a gravitational wave coming out of the screen, and what it does, it momentarily stretches in this direction and compresses in this direction and so on. Okay, so here's kind of in 3D the same thing. That's what happens as a gravitational wave propagates through here. Space gets stretched in one direction and gets compacted in the other direction. Okay, so essentially if a gravitational wave comes at me, I'll feel taller and a bit thinner, and then I'll feel smaller and a bit fatter. Okay, in succession. Okay, well, that would be odd, wouldn't it? I mean, if a gravitational wave came through this room and suddenly this room started doing woo, that would be very odd. So we haven't experienced, I presume none of you have experienced this. I certainly haven't, possibly. So why haven't we experienced this? Well, of course, you probably guessed it. The point is that this is vastly exaggerated, what I'm showing you. The effect of gravitational waves, the stretching and the compacting of space, is a tiny, tiny little effect. Okay, let me show you. So there's a saying that if you put an equation in a talk, you lose half of the audience. So this is the only equation. It's very simple. It's really simple. So let's ask ourselves, what's the size of this effect? So let's imagine you have this perfect circle of size d, or radius d. So by how much does this circle get stretched? That's this delta d here. Okay? So essentially we define this parameter h is called the strain, and the strain is 2 times this delta G divided by the radius. Okay, so 2 times the change in the displacement divided by the size of my circle. And you now go to the physics, you go to Einstein's equation, and you try and figure out what this h, how you can compute this h, and you can end up with this formula here. That's a constant, don't worry about it. That's a constant, don't worry about it. That's the mass of an object. So if I want to make this big, I want to allow a very massive object. Well, the most massive objects we know of are black holes, they're pretty big. But we don't have any, so that's the distance of the object. So I want to make this, if I want to make this big, I have to make this small. So I want a black hole that is nearby. Well, we don't have that many nearby holes, but black holes, but I can estimate sort of at what distance I would see one. And this is the velocity at which this object is moving. And obviously I want to make this velocity as close to the speed of light, that's what the c is, the speed of light as possible. So that's what happens if, for example, we just saw these 2 objects moving around each other. So what we really want is 2 black holes, 2 big black holes, massive black holes, very close by, and orbiting each other, and in fact orbiting each other very closely, because then the speed is very high, very close to the speed of light. Right? If they're very far apart, these 2 black holes, then those speeds will be very low, and give this square here, and then it won't work. So if you plug in some numbers here, in the best case, so you assume some black holes and they're very close and they're orbiting almost at the speed of light. If you put in the numbers in here, then this number h, remember, which is the change in displacement over displacement, comes out to be a number of order of about 10 to the minus 20. Okay, so that's a 0 point, 20 zeros, and then 1. Okay. 0.00001. That is tiny. If you imagine that this circle here was the entire Earth, so the Earth has a radius of 6,000 kilometers, so if I multiply this with 10 to the minus 20, I get 0.1% of the size of an atom. So if I want to detect this gravitational waves, if I had a detector that was the size of the Earth, then what I would have to do is 6,000 kilometers of radius, I would have to be able to detect a change in the size of the Earth that is only 0.1% of the size of an atom, of a single atom. That's crazy. That's completely crazy. Completely impossible. Surely. Anyone who knows anything about physics should say that's completely impossible. And in fact, it was impossible for many, many, many years. In fact, it was so impossible that people didn't think about this even for, these predictions, these calculations were made almost 100 years ago, and people just threw up their hands and said, Einstein made these calculations and said, well, isn't that fun? Isn't this a nice calculation? But obviously this is impossible to detect, period, and went off and worked on something else. Okay? And that was the right reaction at the time. So since the direct detection is very, very difficult, let's have a little interlude and take a little step back. So in the 1970s, let me start. What this picture cartoon is supposed to demonstrate is a particular kind of astronomical object called a pulsar. They're very weird objects, very strange, and I don't want to get into the details. What it is actually a neutron star at the center, and it's not actually very big. It's only about the size of a few tens of kilometers, and it rotates very quickly. Has a very strong magnetic field. That's what these things are, and it shines a beam of radio light, just like this. And the point is that the axis of this beam is not aligned with the axis of its rotation. So what that means is that if you're lucky, then sometimes, if the orientation is just right, then that beam, as the neutron star rotates, that beam will actually hit us once every rotation. It's just like a lighthouse, exactly like a lighthouse. Okay. So that thing is called a pulsar because it pulses. Now you see me, now you don't. Now you see me, now you don't. It goes on and off and on. And those are very interesting. But a particular kind of pulsar was discovered in 1974 using this instrument here. That's the Arquivo radio telescope. It's a 300-meter telescope. Until very recently it was actually the largest telescope on the planet, but now in China they built an even bigger one, 500 meters. And using this telescope, these two gentlemen here, Joe Taylor and Russell House, discovered a pulsar that was not just by itself, but was actually in orbit around a second neutron star. Okay, so they were orbiting each other, as you see up here. Two neutron stars orbiting each other. Only one of them was seen as a pulsar, but we know that the other one was also a neutron star. Both of these neutron stars have about 1.4 solar masses. They're about 2 million kilometers apart from each other, which is about the size of the sun, something like this. And the point is that from when you receive the pulse, you can time these pulses extremely well. In fact, these millisecond pulsars, they rotate so steadily that the pulsing that you see is so precise and so steady that it's actually a better timing device. It's a better clock than even an atomic clock. And in fact, there are talks that atomic clocks may be in fact replaced by a network of pulsars sometime in the future to actually keep world time. But anyway, the point is that I was going to make here is that the arrival time of these pulses, or the rate at which the pulsar is spinning, from that rate, what you can also determine is not just the rate at which the pulsar is spinning, but also the rate at which the two stars are circling each other. Okay? And that time, that orbital time, you can monitor very, very precisely. And it turned out that over the years, as they gathered more and more data on this pair of neutron stars, the orbital period became longer and longer. Okay? What that means is that the two stars must actually, their orbits must be getting wider. The whole system is losing energy. Where's that energy going? It turns out that that energy is, remember this situation, you have two very compact objects orbiting each other. As we've seen previously, well, those two objects must actually be radiating gravitational waves. And those gravitational waves are taking energy away from that system. And that energy is being taken from the orbital energy of the two stars. So these red dots here are measurements, and the blue line that we see there is the prediction by general relativity of how the orbital period of the system should change as a function of time, just due to the loss of energy that is radiated away by gravitational waves. And the two things are spot on. Okay? The prediction by general relativity was spot on. In fact, this was so good that, remember this is back in the 1970s, this is so good that this pretty much convinced everyone that gravitational waves indeed exist. It's not a direct proof, they haven't directly seen gravitational waves, but this system, the behavior of this system, just simply cannot be explained without assuming that gravitational waves are there. And for that reason, those two gentlemen were awarded the Nobel Prize in Physics in 1993. Okay? So if you want, that was already the discovery of gravitational waves, but it wasn't a direct detection of it. But this convinced people that yes, gravitational waves are not just a fiction of theoretical physicists, but it's not just something that's on a piece of paper, but it's something that actually exists in nature. Okay? So that got a lot of people thinking, well, okay, now we have proof that they do actually exist. Let's go back to the drawing board and let's go think about this some more. Maybe there is some way in which we can actually directly detect them. Now that we know that they do exist, and now that I don't have to run the risk of maybe investigating all the technologies of how I might actually directly detect them, and then later on not going to find anything, now that we know that they do exist, let's think about this more carefully. So the idea, remember, so these two compact objects, they generate the waves. These waves then travel through space, they hit the Earth, and remember this is vastly exaggerated what we're showing you, but it stretches the Earth. Now of course we can't use the Earth as a detector, you have to do something else, and what you can do is, what that something else, how the principle of detecting gravitational waves on the planet Earth is shown here in this video. It's called using something called a laser interferometer. So how this works is essentially you have a laser, you shoot a laser beam, and then you separate the laser beam and send it down two paths that are 90 degrees separate, and then you bounce the beam back at the other end, and then you recombine the two light again. And if the two, light is a wave, and if you combine the two waves in one particular way, as you just saw here, and you'll see it in a second, then if you combine the waves in one particular way, then they actually cancel each other out, and you don't see anything here at all. If you shift the two waves by just the right amount, then you do something. You do see something here. So the idea is that if a gravitational wave travels through here and changes the length of these two arms and changes them differently, then the two light waves get shifted backwards and forwards, and the light on the detector here essentially goes on and off, goes on and off. Okay? So that's the principle of how you might be able to detect a gravitational wave here on Earth. So these kind of machines have been actually built. So here are two in the United States, LIGO, it's called LIGO, Laser Interferometry Gravitational Wave Observatory. One is in Hanford in Washington State, so in the northwest of the US, and the other one is in Louisiana in the south. So here you can see the two arms of the interferometer, and these arms have a length of 4 kilometers. And these two things are actually more or less identical, these two observatories. And the reason why there's two of them, I'll explain, you'll see this in a second. So construction of this thing started in 1995. And as we'll see in a minute, first detection was in 2015. Took them 20 years to get the technology right. 20 years. That's, a good fraction of someone's career working on this one project. And that alone should tell you how difficult this experiment is. Okay? Again, remember 10 to the minus 20, 0.1% of the size of an atom if you had the entire Earth. You don't have the entire Earth, you only have 4 kilometers. You don't have 6,000 kilometers of the Earth, you only have 4 kilometers. Okay? 4 kilometers times 10 to the minus 20 is about 5,000th part of the size of a proton. Okay, so for those who know what a proton is, it's a tiny fraction of the size of a proton. That's what they had to detect, is the change in the length of these 4 kilometers, or they had to essentially be able to compare the length of this arm to the length of this arm at a precision that corresponds to about a fraction of the size of a proton. Okay, that's just, whoa, amazing. So that's not the only ones, there are others. So there's one in northern Germany actually called Geo 600, and as the name suggests, 600, the arms are not 4 kilometers long, they're only 600 meters long. So this thing is not actually competitive in the sense there's just essentially tests being done here. Lots of the laser physics that went into LIGO came from here. There's also one in northern Italy, the European, the Virgo consortium. This is near Pisa. This is a similar 3 kilometer arm, so that's similar to LIGO. This is the Virgo consortium. Okay, just again, I don't expect you to read any of this, but I just again want to impress on you how difficult this experiment was. And again, they spent 20 years of their lives perfecting the technology, and there were literally thousands of engineers who worked on this project, perfecting the technologies, and the technologies that have gone into this are just absolutely stunning. I mean, you can imagine that even if there's just a truck going past outside, that truck induces vibrations in the ground that completely kill your entire experiment. So these vibrations are many orders of magnitude larger than the effect that you're trying to see. So you have to insulate your laser and your entire system, and the reflecting thing that reflects the laser back at the end of the tunnel. All of those things have to be insulated from the ground to an extent that a truck going past does not disturb the mass. Right? That's just absolutely incredible. So, this all culminated, 20 years of effort, then culminated in February 2016. There was a press release on 11th February 2016. Here's the original paper. It was published on the 12th of February in Physical Review Letters. Wasn't Nature or Science. In Physical Review Letters. And in this paper, they reported on an event that was recorded actually on the 15th of September 2015. So 20 years after they started working on this project, they detected their first source. It's an incredible paper, it's very well written. It has 900 authors. At least 4 of them are dead already. So yeah, they didn't get to enjoy this for a long time. So what did they see? They saw pretty much exactly what I showed you earlier. They saw 2 black holes. They saw the very last moment of 2 black holes orbiting each other, and because they're sending away gravitational waves, just as with the pulsar and the neutron star that I showed you earlier, the gravitational waves carry away orbital energy, and so they're coming closer and closer, these objects. And eventually, they merge. Eventually, they touch, the 2 black holes, they touch and they merge. Okay? And it's that very last instant of the 2 black holes orbiting each other, that very last instant is what they saw. Okay? Because only then are the gravitational waves strong enough to actually to be able to detect them. So at earlier times, when the 2 black holes were still further apart from each other, the gravitational waves weren't strong enough and they couldn't be detected. But then they were spiraling into each other, they were getting closer and closer and closer, the gravitational waves get stronger and stronger, and then finally, there was a final bang, if you will, when they collided, and it's those moments that they detected. What did that show? Yeah, okay, that's right. That demonstrates just simply how as they get closer and as they spin faster or orbit each other faster and faster, the amplitude of the gravitational waves gets higher, and the frequency, so the wavelength between them gets shorter and shorter, the frequency goes higher and higher. See that now it's stronger, the color gets stronger, that's supposed to demonstrate the amplitude, bang, 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 and that's the final pulse of gravitational waves, and then it's gone. Okay? Once it's merged, it's no longer binary, nothing's moving anymore, there's just the 1 black hole, and that's it. Okay? So after the merger, the gravitational waves just disappear. Okay, so and then you can, this is the same as you saw earlier, what happens as these waves arrive at Earth, again strongly exaggerated, the frequency, the amplitude becomes higher, the frequency becomes higher, and it's gone. Yeah. And this actually happened, that was roughly the right time scale. This is something that lasts, a signal that lasts for on the order of a second. Okay? So here's the original data that they actually detected. So this is from the Hanford detector, this is from the Livingston detector. The squiggly line is the actual data that they recorded, and the more solid line is a model of what actually happened. And what you see here is exactly what you would expect. The amplitude grows, gets larger, and the frequency, so the distance between these between these peaks gets smaller, the wavelength becomes smaller, and the frequency gets larger. So that's exactly what you would expect. And here, this is as a function of time, so this is a tenth of a second, roughly here, where this happened. So actually, you can make this audible. You can turn this into a sound, and when you do, it sounds like a chirp. And let's see if this works. That didn't work. That's not what I expected it to sound. Anyway, this is essentially, it gets louder, and it goes up, right? So it's sound, the chirp sound like that is what happens. Now, since they detected in both detectors, it turns out actually that it arrived at the one detector. I'm trying to remember how much. Was it 0.7 seconds?
Yes, some fraction of a second.
Yeah, 7 milliseconds. So the signal was detected. Sorry, go back. So the signal was detected in one of the detectors 7 milliseconds, so 7,000th of a second earlier than in the other detector. Why is that? Well, if imagine detector 1 is over here and detector 2 is over here. If the signal came straight from you, then the signal would pass both detectors at the same time. If this signal comes from over there, then this one sees it first, and this one sees it later by a time that takes the wave traveling time from here to here. And gravitational waves travel at the speed of light. Okay? But if it comes from some other direction, then there will be some other delay in the signal. And from this delay, you can actually tell roughly where the signal came from, where the gravitational waves came from. Only very roughly. And so in the case of the first detection, this was roughly the area on the sky where it can come from. This is a very large area of the sky. It was, the area was something like 600 square degrees on the sky. It's very large. They did know the distance roughly. It came from an object at a cosmological distance, millions of light years away. And so, of course, what they did is they tried to look at this part of the sky with other telescopes. So they knew there were two black holes merging there, and I'll tell you a bit more about the two black holes in a minute. Two black holes merging there. Wouldn't one expect these two black holes also, to be somehow associated with some other event or something else happening in that distant galaxy that will actually show up in normal light as well? Well, they trained every possible telescope on this area of the sky. Of course, it's a very large area of the sky, so you can't monitor all of this. But they didn't find anything. Okay? There was nothing to be seen. So what these gravitational waves showed us, well, this one detection at least showed us, was an event that was otherwise completely invisible. So with all the other techniques that we have, and all the other technologies that we have to observe the universe, this event remained invisible to us. And only gravitational waves showed them to us. Okay? So gravitational waves here really are opening a window to the universe and showing us things in the universe that we cannot see there by any other method. So what precisely actually was it that we saw there, these two black holes? Let me give you just a little bit more info. So the two black holes were actually of an intermediate size. One was about 29 times the mass of the Sun, and the other one was 36 times the mass of the Sun. So 29 and 36 times the mass of the Sun. We know much smaller black holes, and we know of the existence of much, much bigger black holes, but we've never actually been able to see a black hole of the size of several tens of solar masses. So that was new as well. So 29 and 36. The final black hole that emerged after the merger has a mass of 62 solar masses. So we have 29 and 36, and made a black hole that's 62. 29, 36, 62. Should be 65, right? Why is 62? Where did these three solar masses go? Well, remember, gravitational waves carry away energy. This merger event, or in this merger event, three solar masses were carried away by the gravitational waves in energy. Three solar masses is spectacular amount of energy. Okay, our entire sun produces, what by definition is one solar mass, and will burn a few percent of that one solar mass, and will burn that over a period of, say, 10 billion years. Here we have three solar masses that are completely gone, not just a few percent, are completely gone in the space of a tenth of a second. Not 10 billion years, a space of a tenth of a second. This event, for that short period of time, was 50 times as luminous as the entire universe in terms of electromagnetic radiation. Okay? So in that time, the amount of energy per unit time radiated in this event was 50 times more than the entire universe radiates in the electromagnetic radiation. Okay, that's enormous. So it's a huge amount of energy that is being lost there. Okay, so let's move on. So like I said, the very first one was detected in September 2015. LIGO was operational for just a few months during this time. It detected it during this observing run. It detected right at the start. So this was the first observing run after a technological upgrade of the LIGO detectors. Been upgraded to what's called the advanced LIGO. And they switched it on, and it pretty much immediately saw the first event. Right? That's just amazing. And then there was a second event shortly after, but they're a little bit uncertain about this, so this is just a candidate event, it wasn't a confirmed event. But then a second one was detected in December 2015, and then the run ended. Since then, actually, a third one has been detected. Not sure what I wanted to say with this plot, but let's move on to this plot. This is something about the second event. On the second event, they were actually able to measure, by modeling the signal, the data that they saw, they were actually able to say something about the spin of one of the black holes. Okay? So over here, these are the constraints on the spin of the primary black hole, and these are the constraints on the spin of the secondary black hole. And the secondary can't say very much about it, and this is magnitude, and this is the direction of the spin axis. And you can actually get some reasonable constraints. Okay, so again, this is amazing. So it's a 30 solar mass black hole at hundreds of light years away. You can say something about which direction it's spinning and which magnitude it's spinning. That's amazing. So again, this is that was the second event. So since then, there's been a third event here, which was detected in January of 2017, and so this year. Demonstrate again, this is the first one, 29 and 36 solar masses gave you a 62 solar mass event. This was a much smaller one, and this is slightly bigger again, but in every case, you're losing in each of these merger events, several solar masses was lost and was radiated away by the gravitational waves. And so, again, I said this earlier, so this is really what LIGO has done. You can really compare this with this instrument up here. This is the first telescope that was built by Galileo Galilei, and that he used more than 400 years ago in 1609 to look at the heavens for the first time with a telescope. Okay, he was the first guy to look at the stars not just with the unaided eye, but actually to use a telescope. And that, of course, as you can imagine, revolutionized astronomy and was the start of modern-day astronomy, essentially. And so he really opened up the universe to science, and this is very similar. We're undergoing a very similar experience as what Galileo is undergoing. We've now been able to see these three merger events that otherwise we would not have been able to see. So these gravitational wave detectors have opened up a window to the universe that was completely closed to us before. And as you can imagine, this made a lot of furores all over the news, all over, and the guys are now raking in one prize after the other. So Ron Dreher, unfortunately, just died recently. Kip Thorne and Ray Weiss, they've received the 2016 Gruber Prize for Cosmology, so one of the most distinguished prizes. Similarly, the Breakthrough Prize in Fundamental Physics was awarded to them. They got the Kavli Prize, which I was fortunate enough to be there at the ceremony. That's very interesting, and I think it's no big risk if I make the prediction that they will get the Nobel Prize. I think everyone thinks that they will probably get the Nobel Prize this year. Last year they were just too late. They would have gotten it last year, but the announcement was, I think, 3 weeks too late. Okay, they were 3 weeks after the deadline. Otherwise, they probably would have gotten it last year. Which is very unfortunate for Ron Dreher because he has now died, and their Nobel Prizes are not awarded posthumously. So, what is the future of gravitational wave astronomy? Well, there are different types of objects that might generate gravitational waves, and they range from the black holes that we've just spoke about. We've already talked also about neutron stars and pulsars, all the way to the universe itself has produced, the Big Bang essentially has produced a whole array of gravitational waves. And it turns out that you just simply need different types of detectors to be able to detect these different gravitational waves. So something like a LIGO, an earthbound laser interferometer, is just not going to do it all for us. Okay, there are only certain types of gravitational waves that you detect with this. But if you want to get the whole array of gravitational waves that are presumably out there, you will need different types of detection techniques. But let's just for 1 second stick with the ground-based interferometers. So we have the two LIGO ones in North America. Here's Virgo undergoing also the same technological upgrade that enabled the LIGO detectors to make their first detection. LIGO India is planned, and LIGO Japan is actually being built. The contracts have been signed. So just to show you how it helps to have additional detectors on the planet, all operational at the same time. So these are the 3 detections and the 1 candidate, and again their error bars and where they are in the sky, with just the 2 detectors that we have. If you were able to just add a 3rd detector, it probably would have looked something like this. If you just added the Virgo detector in northern Italy, you would have decreased the error bars a lot. But you can use the same principle of LIGO, of an Earth-based detector, and you can put the whole thing into space. Okay, there's a project called ELISA, an ESA project, which was originally also a NASA project, but it got out. I think now they've re-entered, but yeah, now they got back in. Anyway, LISA is the same idea. Again, you have an interferometer, so the idea is you put a space door, you put 3 spacecraft and into space, and not just anywhere in space, actually put them into orbit around the sun. And this is actually, so the idea is they fly in formation, like as a triangle, and they orbit around the sun, and you have these 2 legs here again, so you have the one vehicle sending out the lasers and the other vehicles reflecting the lasers. And the idea here is that you have that the length of these legs is no longer just 4 kilometers as it is with LIGO, but is now 1 million kilometers. Okay? So again, these things have to fly into in this particular configuration around the sun. One of them will shoot off a laser, which is then reflected by a little 5 centimeter large gold platinum cube that each of these things carries around, and that platinum cube reflects the laser light. In fact, what these spacecraft actually do is, their job is not to touch that cube. Okay, so each of them carries this little cube, and this little cube is in free fall around the sun. They just orbit the sun as they would. And they're in vacuum, in a vacuum chamber, and the job of the spacecraft is just to keep all the mirrors and to keep all the equipment that you need around that cube without touching the cube. That's the job. Okay, so you need the cubes to be in free fall around the sun, just to follow the curved space-time around the sun, and the spacecraft are not allowed to touch or interfere with that free fall of the cube in any shape or form. That's the job. That's incredibly difficult to do all the station keeping. ELISA is planned for launch, I think, in 2034. This is what it looks like inside here, and here I think is where the cube sits in the little vacuum chamber. And if you think this is science fiction, well, it's not actually science fiction any longer, because there was a technology mission called the LISA Pathfinder mission, which was launched at the end of 2015. Here's the launch on the LISA rocket. This mission was put into orbit around the sun, into a spot called L1. Never mind, I'll skip that bit, what that means. But this is what it looks like. So the LISA Pathfinder was essentially the LISA mission in small. It's a pure technology mission, had no science goals. But here's the 2 cubes that I was talking about, this time all in one spacecraft. Okay? And the spacecraft is not allowed to touch these cubes. It's just following around these cubes. Okay? And so here they were actually just testing all this technology, and here's an illustration of the results that they got. These are data. This is essentially how well they were doing. Okay? The lower this line, the better they were doing. And this is the original requirement for a pathfinder mission, and this is the requirement that we need for an actual for the actual ELISA mission. And what you can see is that the pathfinder mission did even better already now, or did better than what you need to do in the final ELISA mission. So that's very, very encouraging. It's really, really good. We talked about pulsars already. You can also use pulsars as gravitational wave detectors, because pulsars are spread throughout the entire galaxy, throughout the entire Milky Way galaxy. And if you monitor pulsars throughout the galaxy, you monitor the arrival times of their pulsars very closely, then as a gravitational wave moves through the galaxy, it will, as it stretches the space along this line of sight, the arrival times of the pulsars will be modified, they will change. And you can see this then as a gravitational wave ripples through the galaxy, you'll be able to see different pulsars change their arrival times as the wave moves through. So this is another detection now, this time you're using essentially the entire Milky Way as a detector. Before we had LIGO, 4 kilometers, then LISA is 1 million kilometer arms, and now you're using the entire Milky Way as a detector essentially. So there are again different international observatories that are participating in this radio observatories in North America, in Europe, as well as in Australia, FAST radio telescope down there, that are all gearing up towards doing this kind of thing and detecting gravitational waves in this way. Okay, so let me finish up with a quote by Ray Weiss, which I hope is going to work here. So this is one of the guys that was central in the LIGO collaboration, and let's see what he has to say.
I would love to see Einstein's face, and he would have been as dumbfounded as we are, because it's a wonderful proof that all this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's an miracle.
He said he would love to see Einstein's face, and I think, thank you.